So, good morning all of you, welcome back for this course. In the last 2 or 3 classes, we discussed extensively about the fundamental concepts of NMR spectroscopy, where I introduced concept of magnetic moment, spin angular momentum and also magnetic moment, and at the same time we discussed about the Zeeman interaction, energies between two different states, degeneracy after we put it in a magnetic field, and then we also discussed about Larmor precision frequencies and what is the Larmor precision frequency, and then we discussed extensively about population difference between two energy states for spin off nuclei. And I said there must be population difference for us to see the NMR signal, and if there is no population difference, there is no NMR. And we also understood that spin angular momentum I is a very important factor to see NMR. If for a given nucleus, if I is 0, they are NMR inactive nuclei and we cannot see NMR for such nuclei. All those things we discussed extensively. We also understood how to induce the resonance by applying a radio frequency signal, and I said the radio frequency signal should be applied in a direction perpendicular to the magnetic field. In this sense, the magnetization or spins will be aligned along the magnetic direction of the magnetic field, and you have to apply the magnetic RF pulse in a direction perpendicular to it. Then the magnetization will be tilted to the another axis. All the 3 x, y and z axes are orthogonal to each other, and the tilting of the magnetization obeys what is called right hand thumb rule. If the thumb points to the direction in which axis in which you are applying the RF pulse, then curly fingers tells you the direction in which the magnetization flips to the particular axis. So, we extensively about application of the RF pulse in different axes, everything has been discussed at stretch in one of the previous courses, but I do not want to go to the details of that, but I just want to tell you we need to apply RF pulse. The radio frequency which we are going to apply is in the form of a pulse, and the pulse duration I said is of the order of 5 to 10 microseconds for proton, and also it is of the order of 10 to 15 microseconds for carbon 13. This is for 90-degree pulse to tilt the magnetization from z axis to x or y axis, and that for 90-degree tilting we apply RF pulse. That is why it is called a pulsed NMR spectroscopy. Okay. It is completely different from what NMR used to be practiced about 4 to 5 decades back, about 50 years back, that is called CWNMR. It is a pulsed NMR, and after we collect the signal we do the Fourier transformation, that is why it is called pulsed Fourier transform NMR. Okay, we discussed little bit of this introduction everything yesterday. We will go further today, and then yes, I wanted to tell you about what I said something about how do we induce the resonance by applying a radio frequency signal, and we saw that the magnetization spins which are in the ground state goes to the excited state, and spins in the excited state comes to the ground state, and the difference in the spin population is what we are going to detect. That is a simple way of understanding, but may not be the right way. As I said, the NMR spectroscopy is neither absorption or emission, it is a coherent spectroscopy. We have to see the coherence of the nuclear spins, and there is a different way of understanding it by using what is called bulk magnetization concept. So, I am going to introduce today the concept of bulk magnetization. This is the real way of understanding how do you see the signal in NMR spectroscopy. Okay. For this we have to understand what is called random phase approximation. Okay. First we look at the individual nuclear magnetic moments. The nuclear magnetic moments which I said mu, they keep oscillating at equilibrium. They are not in steady state. As I said, this nuclear spin starts precessing in the magnetic field, and the oscillation is going on, that is called a precession. As a consequence, individual magnetic moments are not aligned in the direction of the magnetic field. They are constantly changing its position. They keep on precessing like this, okay, like this. This is what we observed. This is what I called as Larmor precision, that is what I explained also. And now we will go into a slightly different way of understanding. As I said, There are two possible orientations for spin of nucleus. One is alpha state plus half, beta state minus half. As I already told you, alpha and beta states are spin up and spin down state, conventionally called alpha and beta. Now consider nuclear spins which are in the alpha state. That means all of them are aligned in the direction of the magnetic field, not exactly aligned, making an angle like this. All these nuclear spins, magnetic moments will be aligning and precessing, making an angle, certain angle theta with respect to the magnetic field. So individually each of them is a vector, and this spin ensemble do not have any phase coherence at all, but they will be precessing. There is no, okay, they are with a cone opening upwards. This is the state of all the nuclear spins which are in the alpha state. Now what we will do is, we will resolve the vector. It is a magnetic moment is a vector, mu is a vector, I told you. We will resolve them into three components, x, y and z. Vector can be resolved into three components. Now when the nuclear spins, the magnetic moments are precessing like this along the z axis in the direction of the magnetic field, which is assumed to be along z axis. Magnetic field is assumed to be along z axis. Now what will happen to the xy components of this? Because continuously they are all precessing, the xy component, if you take the ensemble average, then what will happen? The all these vector components in the xy plane get completely averaged out to 0. There won't be any x and y components, there won't be any magnetization in the xy plane like this. That is what is going to happen. So this is because of random phase approximation. We can make an approximation because of the random phase, all the components in the xy plane are averaged to 0. So we have only nuclear spins or magnetic moments aligned along the z direction. Okay. But now what is the vector addition of all the nuclear spins? In the xy plane here they are averaged to 0, but not along the z axis, they are in the same direction. The vector sum of the nuclear magnetic moments in the z axis will be added up. Only in the xy plane it is 0. Okay. So when all the magnetization is added up, in the xy plane it is 0, no magnetization, it is 0 here, mx and my are mu x and mu y is 0, whereas here everything is there. Now the vector addition of this, I can consider it a small tiny magnet like this. See, a small tiny magnet. This is what is called a bulk magnet. I consider a small tiny magnet like this. All these magnets along the z axis, this vectors of magnetic moment vector along z axis, we quad up and get a small magnet like this, which is aligned along z axis. Okay. And xy component is totally 0, fine, that is okay. Now we will go to a situation like other spin, all the nuclear spins which are in the beta state. As I told you, in the beta states they will be opening cone, like a cone opening downwards. Again if you take the ensemble average, again I can resolve this beta into three components, magnetic moment oriented along beta into three components x, y and z. Because of the random phase approximation, all the components of the vector along x and y are averaged out to 0. There won't be any magnetic moment along x and y direction. Again on the minus z direction, all of them get added up. That is what is going to happen. And then we are going to get a small magnetization, small tiny magnet along minus z direction. Remember, for all the magnetic moments which are orient in the direction of the field, for alpha state there is a tiny magnet generated because of the vector addition and with random phase approximation along z axis. For beta spins it will be magnetization or tiny magnet in the direction opposite to the magnetic field. Now we have two magnets, small tiny magnets for two spins, two spin states, one along z axis, other along minus z axis. This is the concept. But remember, I also said there is a small population difference between alpha and beta states. That means the magnetization along plus z axis or this tiny magnet which is along z axis is more than that along the direction opposite to it. Now, if you take the difference of these two, again it is a vector addition. Difference of the magnets between plus z direction and minus z direction, if you take, there is a small net magnetization. There is a magnet, tiny magnet along z axis. There is a net magnet. This is what is called magnetization. It is called bulk magnetization. Concept of bulk magnetization comes because of random phase approximation. All the xy components of the alpha and beta spins states, all the vectors along alpha and beta vectors average out in the xy component. In the z axis there is a co-addition because there are excess spins, excess population along z axis. The difference gives us a tiny magnet which is called a bulk magnet. We call it as bulk magnetization. Okay. And this is usually denoted as m naught. All right. And always it is oriented parallel to the direction of magnetic field. A static magnetic field B naught is there, huge magnet, along that direction it gets aligned. Now, this can be treated like a tiny magnet. Unlike individual magnetic moment vectors, they were always continuously changing, rotating, processing along the direction of the field, but this bulk magnet is always static. It is stationary, it is not moving. In equilibrium it is stationary and mx my component is 0, whereas mz component, which is equilibrium, which is also called m naught, equilibrium magnetization, are equal to mq, whatever you call, is non-zero and it is stationary. It is not moving. Remember, individual magnetic moments are moving. When I take into account the random phase approximation, then I can generate a small magnet, tiny magnet, because of the difference in spin population and addition of vectors along z plus z and minus z. Then this tiny magnet is a bulk magnetization which is stationary along z axis and is perfectly aligned along z axis, along B naught field. Okay. Now, if I have to detect a signal in NMR, what we have to do? We have to create what is called a non-equilibrium state. Remember, in the equilibrium state, the magnetization is aligned along the z axis, aligned perfectly aligned along the magnetic field direction. Now, if I have to detect the signal, I have to create what is called non-equilibrium state. How do you create that non-equilibrium state? There is a way of creating. That is by doing what is called application of an oscillating RF field in the direction perpendicular to the magnetization, bulk magnetization. Let us say this is z axis and bulk magnetization is here. You have to apply in a direction perpendicular to it, either in the x axis or y axis you have to apply and apply RF pulse, so that the bulk magnetization can be tilted. There you create a non-equilibrium state, you will perturb this spin system. Okay. How do you do that? By applying a radio frequency pulse. This is what I said. We apply a radio frequency pulse in a direction perpendicular to it, which is the order of 5 to 10 microsecond, to tilt the magnetization to x or y axis, called a 90-degree pulse, especially for protons. Okay. And the frequency of oscillation, as I told you already previously also I said, this should be exactly RF pulse frequency should match with the Larmor precision frequency. Then there is going to be a resonance. You are going to tilt the magnetization, bulk magnetization. And tilting of this bulk magnetization, you can do it with a different flip angles. That is what I said last time. In the previous class I said we can tilt the magnetization from z axis to x axis to y axis minus x axis and again take back to z axis. I can make the magnetization to come from z axis slowly like this and take it back to z axis. I can make it keep on rotating, keep on applying the pulses 90, 180, 360, 270, 360 like that. You can make the magnetization to go round and round. That is what you can do. And this is that angle, this is the equation which we have to use. This is the angle theta, and how much is the magnetization tilted by 90 degree or 180 is defined by this equation. Okay. This is called gamma B1 into Tp. Gamma B1 is called the RF power, Tp is called the pulse width. So, it means the power and the pulse width defines the angle of tilting of the magnetization. If I have to tilt the magnetization by any angle, by angle theta, then I have to manipulate, I have to play with the RF power and I have to play with the pulse width. If I can do that, I can tilt the magnetization from z axis to any angle. Okay, that is what we can do. Now, let us consider the equilibrium magnetization is along z axis. I will show you how we can tilt it. I am going to apply a 90-degree x pulse. That means, I am applying a pulse along x axis a 90-degree. What do you mean by a 90-degree pulse? That pulse should be sufficient enough to tilt the magnetization to, if I applying along x axis, it will tilting along minus y axis, because of the right hand thumb rule I told you already. So, it has to tilt towards minus y axis. This is the direction in which I am applying the RF pulse, and the magnetization which was here tilted to minus y. I increase the width or power of the pulse such that I can make it a 180 x pulse. Then the magnetization start tilting to minus z axis. From plus z it came to minus z axis. You can see here from plus z with 180 pulse shifted to minus z. Now, I increase the power in the pulse such that I can take the magnetization completely on rotation like this. From z axis I can rotate by 270 degree, from plus z it comes to minus y, then minus z, and then to plus y, and then apply a 360 pulse, it will completely go one round, one rotation like this. See the beauty of it, and this is what happens. This is why we can call it as this is called a flip angle of the pulse. I can apply different flip angles of the pulses and tilt the magnetization by any angle theta with respect to from the z axis with respect to x or y axis. This is what is the concept we have to use for understanding NMR. So, we have the bulk magnetization which is stationary has to be perturbed by applying a RF pulse at any angle x or y axis in a direction preferably perpendicular to it, so that x or y axis if you apply by any angle you can tilt the magnetization, and this is how we can rotate it in the anti-clockwise YZ plane. Of course, you can apply in the other direction and rotate in the other direction, and instead of x axis you can apply on y axis. All possible combinations you can think of. Okay. Now, I am going to introduce what is called the free induction decay, and how do you get the NMR spectrum. Look at it, after the 90-degree pulse what happens? The entire magnetization is brought to XY plane. See, magnetization which is a tiny magnet which is some of the z component vectors, magnetic moment vectors which we already discussed, the magnetization comes to the x or y axis or xy plane, and as soon as you bring it to the x or y axis, there is what is called instantaneous phase coherence. All the spins are aligned along this axis, particular axis. There is complete phase coherence is there, but what happens? This phase coherence is not maintained for a long time. The spins start undergoing dephasing, which was here brought here, then start moving, different nuclear vectors start moving like this. They will completely get dephased in the xy plane. After that dephase in the xy plane, because it is a perturbed system, from equilibrium you are perturbed, it has to go back to equilibrium. Then while undergoing decay in the xy plane, it start going back along z axis. It grow along z axis, okay, and this is an exponential function. Both decay in the xy plane and growth along the z axis, both are exponential functions, and this is pictorially you have to understand. I bring the magnetization from z axis to x or y axis. I am looking, sitting here, I am observing magnetization, but you see with time there was an instantaneous phase coherence, all the vectors were along this axis, but the phase coherence get disturbed. You see this internuclear vectors, all the magnetic moment vectors start dephasing, they start spreading in the xy plane. Simultaneously there is a decay and they will start growing along this axis. Both are simultaneously happening, decay and growth, and you see if you look from the top of the magnet, it appears for you as if there is a spiral going on like this. It is like decaying in the xy plane, simultaneously start growing along z axis. And when it is happening, when I am sitting here in the using electronics, I collect how the signal is decaying in the xy plane. I apply the RF pulse, then I will keep quiet. The magnetization which was disturbed will decay in the xy plane, start going along z axis, and it is an exponential function. When it goes back, I am going to have a receiver here. It induces EMF in the receiver coil, and I am going to collect that as a function of time. Okay. This is it will be freely processing after I apply the radio frequency pulse, and you are not doing anything, it is free. At the same time, it is decaying while inducing EMF in the receiver coil. That is why it is called free induction decay. It is called FID, and it is exponentially, it decays like this as a function of time. This is what we are going to collect in the NMR spectrometer, and this is a conventional one dimensional NMR spectrum is like this. You apply a radio frequency pulse, RF pulse, and give a small short delay just to make sure there is no dampening and everything. So, and afterwards you start collecting the signal like this as a function of time. This is what is called acquisition time, and you give enough time here for the nuclear spins to attain equilibrium. That is called a relaxation delay. So, you have a relaxation delay, apply a radio frequency pulse, and then start collecting the signal. This is basically the one dimensional conventional NMR experiment that is being done. Okay. Now, the question you may ask me is, do we need a 90 degree pulse always to generate the free induction decay? Remember here in this I showed you, you apply a 90 degree pulse and then bring the magnetization to XY plane and start collecting FID. But the question is, do we always need 90 degree pulse? The answer is no, because you can see here initially the magnetization is along Z axis. I can tilt by any angle. I told you gamma B1 T tau p I told you equal to theta. I can adjust the power and the pulse width in such a way I can tilt the magnetization instead of x axis by small angle theta. It is a vector resolved into two components, and this is what you are detecting. So, there is a component here. This component along sine component we do not require at all, we do not collect it, whereas the cosine component we are going to collect it. There is some signal. Now, increase the theta, is small value to more value, now 45 degree let us say, the component along this axis become more, and go to 90 degree, the entire magnetization is brought to x axis from z axis. This is a 90 degree pulse, there is maximum signal here, and then go 180, since you are sitting here, signal is here, you do not see anything at all. So, 180 pulse will not give any signal. Maximum signal you are going to see is only when you apply 90 degree pulse. When you apply 180 degree pulse, you will not see any signal in NMR. Please understand, 90 degree pulse is the one which gives you maximum magnetization, maximum perturbation you can do for the spin system is this, where you are going to collect maximum signal. Okay. Now, FID will be created by an RF pulse of any flip angle, that is what you should remember, need not be 90 degree. But for better signal, more signal to be collected, 90 degree is better, because entire magnetization will be along x axis or y axis where you are keeping a receiver. Do not apply 180 pulse, because 180 pulse will not give signal, and there will be always some component to in the transverse plane to detect the signal. Fine. Now, you have collected the signal. What are you going to do with that? See, they are all time domain signal. There are lots of frequencies present in that. But how do you know what are the frequencies present? So many transitions could be there, so many energy levels could be there in the given molecule, a lot of different nuclear spins could be there. How do you distinguish the frequencies present in that? See, for example, our ears cannot hear or identify all the frequencies at a time. See, it is like a particular music, for example, particular sound you can hear, but all of a sudden if there is a huge noise, you do not know who is talking what. To overcome this, there is a mathematical formula which is given by Jean-Baptiste Fourier. What we do is this called Fourier transformation. We can do Fourier transformation of the time domain signal. The time and frequency are called Fourier pairs. I can do the Fourier transformation of the time domain signal and get the frequency. I can do the inverse Fourier transformation of the frequency domain, go back to time domain. Both are possible. They are called Fourier pairs. So, what I am going to do is we collect the signal like this in the time domain and do a mathematical operation like this called Fourier transformation from time to frequency, frequency through time to frequency or frequency to time, both are possible. And then when you do that from time to frequency conversion by doing Fourier transformation, you get a spectrum like this. This is what is really you see when you record the NMR spectrum. This is what you are going to see, real NMR spectrum. This is called one dimensional NMR spectrum of particular nuclei. I have taken the example of proton here. Let us say it is a proton NMR. If you have some molecule, you give it to the NMR spectrometer to an operator, what he will do? He will put the sample in a magnet and apply a radio frequency pulse, collect the signal in time domain like this, and then do the Fourier transformation. He will give you a spectrum like this. This is finally what you are going to get for our interpretation. Okay. Now, you have got the NMR resonance, NMR spectrum you obtained. This is what all of us will get. Now, the question is, what is the type of spectrum we are going to get? We have to understand there are some intricate details are there. If you take two energy states, are they well defined states? You have understood the Heisenberg uncertainty principle, according to which there is a spread in the energy level. It is not well defined in a state like this, there is a spread in the energy states. Okay. Now, I consider two spin states, alpha and beta, and I calculate the energy difference delta E, and of course, we know delta E into delta T is greater than or equal to h cross is the uncertainty condition of Heisenberg. E energy and time uncertainty is there, that is given there. Now, the detected NMR signal because of this is not a delta function. If it is a delta function, there is no width, it is sharp at exactly at the 0 value, length is infinite, anything above outside this it is 0. So, that means there is no width at all for delta function. The NMR signal is not a delta function because it has got natural line width. Why this natural line width is coming? It is due to the lifetime of the spins in the excited state. How long it stays in the excited state, okay? That is what defines the width of the NMR peak. If let us say delta is larger, okay, then this may be smaller. This is smaller, this may be larger, both are possible. Okay. So, now we will see if the shorter is the lifetime of the nuclear spins, if the spins do not stay in the excited state for a longer time, if it decays very fast, then what will happen? From this equation, the lifetime and the excited state, this is smaller because this condition has to be obeyed, there is a spread in the energy state. Okay? There is spread in the energy level. As a consequence, then if I have a peak like this, I can get a resonance from here to here, I can get here to here, I can get here to here, here to here. Varieties of possible transitions are there because of the width of the energy state. And since if it does not stay for a longer time, this spread becomes more, the line becomes broader. That is what is going to happen. The shorter the time, the spin stays in the excited state, broader is the signal, peak width becomes broader. That is why if you want to see NH and OH peaks in your molecule, if I take proton NMR spectrum and say NH peak and OH peaks, they are usually broad because nitrogen 14 and this oxygen, these are all quadrupolar spins. These quadrupolar spins ensure that the spins relaxes faster. That means the lifetime of the spins in the excited state is very short. As a consequence, you will see NH and OH peaks in the spectrum are usually very broad. Okay? That is the about the lifetime. Now, we can also discuss about what is called selection rules. Any spectroscopy for that matter will have what is called a selection rule, that is the transition that are allowed between different energy states. Since that now time is getting up, what I will do is I will stop here, we will come back to the this one later in the next class. But today what we discuss in this class is we started discussing the concept of bulk magnetization. by using random phase approximation, we understood that alpha and beta spin state magnetic moment vectors can be resolved into 3 components. Because of the random phase, xy components completely get averaged out. There will not be any components of magnetic moment vector in the xy plane, whereas the vector addition will be there along z axis, similarly along minus z axis for the beta state. Due to excess population in the alpha state compared to beta state, there is a tiny net magnetization that is developed along the direction of the magnetic field. And I said the bulk magnet, this is called a bulk magnetization, which is always parallel to the magnetic field direction, and it is static, it is stationary. To understand the NMR signal, if you have to get the NMR signal, this static magnetization, which is stationary, has to be perturbed. How do you perturb it? By applying a radio frequency signal in a direction perpendicular to the z axis, either x axis or y axis. Then as a consequence, the magnetization will tilt to x axis or y axis depending upon where you are applying. By using right hand thumb rule we can understand, and the signal, as soon as you bring it to the x axis or y axis, there is an instantaneous phase coherence. That means all the nuclear vectors are on the particular axis, magnetic moment vector. Then with time they start dephasing. While dephasing, simultaneously they start growing along z axis. Both are exponential processes, it can happen, and when it decays with the time, we are going to collect the signal as a function of time. The signal we are going to collect, and time and frequency are related to a mathematical operation called Fourier transformation. We do Fourier transformation, then the time domain signal will be converted into frequency domain signal, and the number of peaks correspond to different frequencies present in the molecule of your interest. Each peak corresponds to a particular frequency, and that is what we are going to get. That is the real NMR spectrum. And this, as I said, this NMR spectrum, if each peak, if you consider, they are not delta functions, not that line width of each of these peaks is 0. There are certain line width for each of these peaks because of the natural line width coming because of the Heisenberg uncertainty principle. Delta E into delta T is greater than or equal to H cross. Shorter the time the spin stays in the excited state, broader is the signal. And usually, as I said, for OH and NH peaks which are attached to nitrogen and oxygen, which are quadrupolar spins, quadrupolar relaxation is faster. It ensures that the spins relaxes faster from the excited state. As a consequence, if you take the proton NMR spectrum of any of your molecule containing OH groups or NH groups, usually these peaks are very broad. And then afterwards we said we need to understand the transitions which are allowed, and there is a selection rule for this, and that is what we are going to discuss in the next class. Thank you very much.